Hello, worldly crazy people out there. My name is Michael. I like wizards and dragons and making games, and welcome back to 3D Collisions in GameMaker. The last two videos in this series have been about setting up spatial hashes as a 3D collision world hierarchy and adding objects to a spatial hash, and that was a lot of code. And today we're going to write more code, and we're going to implement the remove method for an object in a spatial hash, and I'm going to implement the check object and check ray methods. And that's going to be varying amounts of work. So when it comes to removing an object from a spatial hash, there are two things that can happen. One, well, I guess three things that can happen. One is that the object does not exist in the spatial hash. And if that's the case, then that does make our job easy, doesn't it? And two is that the object might be in the list of planes, the list of infinite objects, and not as part of the main structure. And we can handle that nicely and easily. I'm going to handle that case first. So if array get index in the self.planes list of objects is not equal to -1. Is that not equals? That's not equals. Then we can array delete from the self.planes list. I suppose it would make more sense to save that as a variable and use the variable instead of calling the function twice. So if the object exists in that list, we can simply delete it and return because it's not part of the main data structure. The second thing that can happen is that the object is actually not in the spatial hash, and if that happens, so if not self.contains the object, then it simply would make sense to return and not do anything because the object is not contained in the spatial hash and therefore cannot be removed. And the last thing that can happen is that the object can exist in the spatial hash, and we can say var location is going to be self. All right, you know what? Probably going to have people rolling their eyes at me for not just doing it like this the first time. But instead of having contains return a true false, we can just have contains like return the location to begin with. And in some ways, you can still treat it like as if it returns a true false, but
hey,
it will mean a little bit less, redundant code. All right, that's a little bit more convenient way to type this out, I think. So our location is going to equal self.contained. We'll do it the same way here. If location is not equal to, I guess in this case it would be location equals undefined, then we can return. Otherwise, we can, shall I say again, what was it? Bounds min, bounds max? Bounds min and bounds max. Bounds min is going to be location.get min. Our bounds max is going to be location.get max. And we can do another one of everyone's favorite construct in computer science, the triply nested for loop. And I'm just going to copy and paste the loop because I really don't feel like typing that out again. And we can start from here. So we're going to loop from the bounds min to the bounds max on all three axes. We can say chunk is going to equal get chunk ijk. And we can say chunk.remove object. And that's just going to return, that's just going to call the remove method on one of the spatial hash nodes, which is in turn going to delete it from its own internal list. You could check if chunk equals undefined before you do this, but there's really no point because, as I said, if you use the system correctly and only use the add and remove methods of the spatial hash as a whole, and you don't try to mess with its internals, that will never happen. And I suppose for good measure, you can also, if a chunk is now empty after its last object has been removed, you can just remove it from the lookup table as a whole. I believe I did write a remove chunk method last time. That would be a minor optimization, but just for the sake of not even having to look at chunks that don't have anything in it, could be nice once in a while. I guess I will write a size method in the spatial hash node, return array length. And when you remove something from a chunk, you can say if chunk.size equals 0. We can remove a chunk from I, J, K. So you might also want to attempt to shrink the bounding box of the spatial hash as a whole when you remove an empty chunk, but that's a math problem that I don't know of a good solution for besides like recalculating it by looping over every single chunk in the structure, which seems a little bit less than ideal. So I'm just gonna leave a comment about it here and not actually implement that part. You may want to... Alright, I'm just going to leave a comment about that. And lastly, we can remove our object record. So when we remove an object from the spatial hash, we would like to get rid of its object record. We are going to once again take the object ID, which is just going to be the pointer of the object turned into a string, and we can variable struct remove self.object record and the object ID. And what else do I need? I need to commit this change for one. I did remember to create myself a new branch this week. Checking objects. So before I implement the check object and check array methods in the spatial hash as a whole, I'm going to do it in the spatial hash nodes in the chunks themselves because that's going to be noticeably simpler, and I'd like to start with simple things if I can. So when it comes to checking a chunk for checking a node for a collision, really all we have to do is loop over the object list, check each object for collision against whatever the incoming object is, and then if a collision is found, you just return true. We can do this with, say, for var I equals 0, I is less than array length of the objects array I plus plus. If self.objects index I dot check object against the object, and you also take the group as well, don't you? You do not? Oh, you know what? Did I set that up wrong at the beginning? Yeah, okay, so it's only the check the raycast method that'll take a collision filtering group. It's not the regular check object, because objects themselves already are aware of their collision master and collision group. Okay, that minorly simplifies some of the things I have to do. Or not do, I guess. So if any of the objects in the array detects a collision, you can return true. Otherwise, if none of those detect a collision, you can return false. I'm just going to get rid of the group argument from spatial hash's check object. Since I last really messed with this 3D collision system, GameMaker has added a number of functional array functions, and one of them is array any. Is that its name? Array any? And if you really like functional programming, you could use the array any function to loop over an array and do this. And likewise, there is check array, which is going to be very similar, except we won't be able to simply return once we detect any collision anywhere. I'm going to have to update the actual function that's called, so I'm going to have to call check ray with the ray hit info and the group, because here this is not automatically taken care of. And when it comes to checking array, you are going to want to find the closest hit location. So you're going to have to loop over every single object, no matter how many collisions are detected. And you're going to use the hit info struct to figure out which is the closest. And instead of returning true, we're just going to say var hit detected is going to default to false. If a hit is detected, we're going to set that to true, and then we're going to return hit detected at the end. And that is going to be our raycast. So very similar to other check object and check rays of nodes of other types of collision hierarchy. But there's something that we're going to need to add all the same. And now we can move on to the spatial hash as a whole, check object and check ray. So check object is going to be pretty straightforward. So first, I guess I'll do it in a similar way to the remove method. So first we can loop over all the planes, all the infinite objects, and check for collisions there. So we can simply say for_var I equals 0, I is less than array length self.planes I plus plus. If self.planes index I dot check object, we can return true. Otherwise, I'm going to need to get the bounding chunks of the object. Boy, how did I even do that? The first time. So it's all right. I guess like copy and paste from up there, and we can say the bounds is going to be the get bounding chunk of the object that we're looking at. Bounds min and bounds max are going to be relevant for what we are looping over. We're also going to want to get the chunk at any given location. In this case, we are going to need to check if a chunk is undefined before we process it, because when we're checking an object against a chunk, there is not guaranteed to actually be a chunk at that position. Nothing has been added at that location yet. So if chunk is not equal to undefined, we can say if chunk.check object against our object, we can return true. Otherwise, you're going to have to proceed to check all the other chunks to see if there's a collision. And once we are finished with that triply nested for loop, we can return false. If we get through this entire loop without detecting a collision, we can return false. And let me consult my notes to make sure that there is nothing that I forgot. I don't think there is anything I forgot. Checking the infinite object list, getting the bounds of our object, and looping over the spatial hash. That all looks good to me. So I can commit that change. And lastly, it's going to be raycasts. So raycasts, you may remember, took about 50 years off my lifespan when I did them with a few of the other collision shapes, like capsules or triangles. And indeed, when it comes to raycasting through a spatial hash, I'm going to have a lot more gray hair when I finish this than I did when I started. So let's do this in pieces. So the check ray method on the data structure as a whole is a little bit different from the check ray methods on the individual shapes. So instead of passing in a hit info struct by reference, we are going to create one by saying hit info is going to be equal to new raycast hit information. And we're going to pass this in and out of the various raycast checking methods. And if a hit is detected, it'll automatically update its hit information for like the collision position and normal and that kind of thing. First, what we can do, and we'll do this in pieces, as always, to make this a little bit more sane, is we can check the ray against one of the infinite objects. So we can loop over the array of planes or whatever, and we can, for each object in that array, say planes index I dot check ray against the ray, taking the hit info and with the collision group information. Let's see, if this function returns true, I actually don't have to do anything if this returns true. All I actually have to do is check the ray against the planes. If the hit is detected, the result will be stored inside the hit info struct. So next, I'm going to check the ray against the bounding box of the spatial hash as a whole, and that is going to be, one, how I figure out if it's even worth checking anything inside the spatial hash to begin with, and two, if the ray does pass through the spatial hash at any point, where its exit point is. Unfortunately, I'm going to need to construct a second hit info struct for this because I can't use the first one because I don't want any potential information from checking it against the planes to be overwritten. So we can say, let's call it bounds hit info is going to be a new raycast hit information a second time. And we are going to raycast the bounds hit info against self.bounds.checkRay, and the ray is going to be, again, the ray that we're using, and the hit info is going to be bounds hit info. And that is going to tell us whether or not the ray actually passes through the spatial hash at any point, not counting the, the planes. So if that doesn't happen, we can exit early. So we can say if bounds hit info, and I want to say it, stop doing that. I want to say it's a point. All the values in here should be initialized to undefined, correct? So if shape is undefined, or point is undefined, or distance is infinity, I'm just going to say if bounds hit info.point equals undefined, that means that we do not pass through the spatial hash. If we don't pass through the spatial hash, we can just return the results from checking the ray against the any planes, and we can say if hit info.point is equals undefined, then we can simply return undefined, because this method is going to return undefined if nothing is hit. Otherwise, we can return hit info. This can be simplified in a couple of ways. You can either drop the else, or you can use a conditional operator to simplify that. Now this is where the fun begins. So we are going to, if we don't have any chance to exit early, we are going to want to walk through the spatial hash, chunk by chunk, cell by cell, in the direction of the ray until we exit the spatial hash. So first, and I really need to stop using the words chunk and cell interchangeably in these videos, but my notes say cell everywhere, so I guess I'll try to say the word cell out loud as I talk through this. First, I'm going to get the current cell, so the cell in the spatial hash that the ray starts in. So I can say var current cell is going to be equal to ray.origin, and I guess it was a good thing that I went ahead and implemented the rounding methods in the vector classes that one time in the last video, because I did make a note of that apparently in my notes. So now I feel a little bit silly for making fun of the whole idea when I did get bounding chunk up here, because all other things being equal, this honestly is a much less messy line of code. And I'm also going to need to do the same thing. I'm going to call it last cell. It's going to be ray. No, it's not going to be ray. It's bounds hit info dot point dot div self dot chunk size dot floor. So this is going to be the same logic, but instead of on the ray's starting point, it is going to be at the point where the ray exits the spatial hash. We are now going to step through every cell in a line between the current cell and the last cell, and actually doing that is a little bit easier said than done. This is a problem that is surprisingly similar to rasterization, like how the GPU will do things like draw a line. It's going to be a lot of arithmetic. It's not going to be any really complicated math, but it really is going to be a lot of arithmetic. And I'm expecting to be here for a while while I write this, let alone test it, because it's going to be like when you have a lot of arithmetic, it's really easy to drop a plus and a minus somewhere where they don't belong and spend a half hour searching for that. Anyway, the first thing I'm going to do is figure out what general direction our line is going to be traveling in. So I'm going to say var dx is going to be the sign of the ray.direction.x. Direction, hello. Var dy is going to be the sign of ray direction y, and dz is going to be the sign of ray direction z. And while you're on the subject of just adding more and more just math methods to the vector class, you can totally turn this into, you can totally write a sign method for vectors as well, but I'm not going to. Next, if we can simplify this just a little tiny bit, if the current cell and the last cell are axis aligned, so if they start and the end on the same either x coordinate or y coordinate or z coordinate, for example, if current cell.x equals last cell.x. We can simply set dx to 0 so that we don't take a step in a direction that we don't need to take a step in. And once again, pretty much everything that I'm going to be doing for the next probably 10 or 15 minutes is just going to be a bunch of mirrored lines of code for X, Y, and Z. There will be places in here where you could probably use, like, your vector library to simplify this a tiny bit, but there comes a point where it's just going to be so much arithmetic anyway that I don't really think it'll make things that much nicer. Next, we need to figure out our cell boundaries. So we need to figure out, as you take your ray and as you walk from the ray's origin to the point where it leaves the spatial hash bounds, how far you should step in any direction and how much you should step in any direction. You need to figure out where the boundaries are, and if you exit one cell, you need to figure out where the next cell that you have entered is. So that could mean adding 1 on the x-axis or y-axis or z-axis. That could mean subtracting 1 on the axis, depending on the ray's direction. So I'm going to define a few more x, y, and z variables. I'm going to call this step x, and this can be, we can say if dx is less than or equal to 0, then step x is going to equal 0, else step x is equal to dx. There's a couple ways you could write this out. You could write it out like this. You could use a conditional operator. You could say step x is equal to, if the term dx is less than 0, then step x is going to equal 0, else step x is going to equal dx with the conditional operator. Or you could use the max function. So you could say step x is going to be the max of dx and 0. And I think that's what I'm going to do just for the sake of brevity. Step y is going to be the max of dy and 0. Step z is going to be the max of dz and 0. And we can use that to work out the actual boundary of the next cell. So I'll just say next boundary x is going to be equal to the current cell.x plus step x multiplied by self.chunk size. And once again, we're going to do the same on the other axes. XYZ, XYZ, XYZ. By the time I'm finished with this, none of these are going to sound like real letters anymore. Next, we're going to want to figure out how far the ray can go in any given direction before it crosses a boundary on the x, y, and z axes. This is going to be a bit of a longer line of code, but it's also going to be very important to not screw up, so I better be careful as I do this. So I'm going to abuse some conditionals again. This one can't be simplified to just a min or a max function or anything nice like that, but I'm going to say max x is going to be an expression of ray.direction.x is not equal to 0. So if the x component of the ray's direction is not 0, max x is going to be next boundary x minus the ray's origin.x divided by the ray's direction.x. I'm going to put this in parentheses as well. And if the ray's direction is equal to 0, this is just going to be infinity. You may end up with infinity anyway, if this term is 0, because dividing by 0 in GameMaker, according to the floating point spec, will give you infinity. But dividing by a 0 and just assuming that you'll get infinity just doesn't feel right, even if, like, logically you know that GameMaker will give you infinity. Let's see, next, once again, we can do the same with y and z. If you've ever done anything like, not a true raycast, but if you ever just wanted to like figure out where a ray like coming out of your first-person camera or anything like that intersects the ground, you probably done something remarkably similar to this. So you'll take like the height of the camera, divide it by the cosine of the pitch, and then use that to figure out how far your ray is going to go before it hits the floor or anything like that. I think I did that in Bombardier. Anyway, the last set of terms we have to define is how far we're going to have to look ahead before the ray crosses a cell boundary. I'm gonna call this... I just like gave it a letter in my notes, but I don't really like that because I'm gonna have to say this out loud. So let's call it look ahead. X is going to be equal to another conditional operator. Ray's direction is not equal to 0. Again, fending off some division by zeros. So if the Ray's direction.x is not 0, we're going to return rounded down chunk size divided by ray.direction.x times dx. And if Ray's direction x is equal to 0, we are simply going to return infinity. And we can figure out our look-ahead values for y and z. And before I write any other code, let me just scroll back just to make sure that all my x's, y's, and z's are in the right place. Because it is very easy when you're copying and pasting these lines like this to forget to change one of them or change one of them to the wrong values. But it looks like everything is in working order. Okay. So first, before we start walking, we are going to actually need to check our starting cell. And after that, I'm going to throw... I think I'll use a do until loop. This is a rare instance of a do until loop actually being useful. But first I'm going to check our starting cell, and I'm going to say var chunk is going to equal a self.get chunk. Let's call it current cell.x, current cell.y, current cell.z. We can say if chunk is not equal to undefined, we can check the chunk. We can say chunk.check ray, taking the ray, the hit info, and the collision group. If this is true, if the ray hits something that is residing in the first chunk, then we can return the hit info, because there can't be anything closer. Either you've hit one of the planes, in which case the hit info will store that information, or you've hit something in the first chunk, or you haven't hit anything and we need to actually start walking. You know what? Can I like rearrange this? The only thing this code needs in order to run is to figure out your starting cell. So you could skip a fair amount of arithmetic if you first check your current cell before you do anything else. So that might be worth doing. Okay. So I said we're gonna use a do until loop. This is not something that you see often. You could reformat this to use a while loop or something else, but I don't have anything against a do until loop, so I'm just gonna use it. We checked our starting cell first, we got that out of the way, and then we can update our position. We can check our new cell, we can check our new chunk, and then we can keep doing that until current cell.x equals last cell.x. You know what? I can just say current cell.equals last cell, can't I? So when we reach the endpoint, when we reach the point where the ray exits the bounds of the spatial hash, we can stop. Until then, we can do a little bit of math, and we can say if max x is less than max y, and this is going to be one of those sections where Drago just has a bunch of math words and tries to get it over with as fast as possible. So if max x is less than max y, if max x is less than max z, then we can say current cell.x plus equals dx. So we can add or subtract 1 depending on the ray's direction, based on the sign of the ray's x component of its direction. We can say max x plus equals look ahead x. Else, if max z is greater than or equal to max x, we can say current cell dot z plus equals dz, and we can say max z plus equals look ahead z, like this. Else, if max y is greater than or equal to max x, we can say if max y is less than max z, then we can say current cell dot y plus equals dy, and max y plus equals look ahead y. Else, this is where we're going to be updating our z, so that's going to be the same as this term. Current cell dot z plus equals dz, max z plus equals look ahead z, and this is going to take steps in the direction that the array is going. And if you have reached the boundaries of one cell, we will update the cell that we're currently checking by 1 or -1 in whatever direction it happens to be relevant. And we're going to keep walking. And lastly, after this big ol' if else block, we can get our current cell. We can say chunk is going to equal self.get chunk, and this is going to be a lot like what we did up here. So chunk is going to be a get chunk current cell.xyz. This is our current position where we're currently walking. If that chunk is not equal to undefined, if chunk.checkArray, that means we hit something. And since we're advancing outwards from our origin, we're taking steps outwards from our origin. The first hit that you detect in this process will be the closest one, so you can simply return the hit info. We're going to do that until our current cell is equal to our last cell. That's where the array exits the spatial hash. For some of the other collision detections, we might say that at this point we can simply return undefined. But remember, it is still possible that we've actually hit something. It is possible that we've hit one of the planes up at the top. So what I'm actually going to do is say if hit info dot point that we collided with is equal to undefined. We're simply going to return undefined in that case. Otherwise, if it's not undefined, we can return hit info. And we can return the results of whatever plane it hit. So given that we are taking a bit of a long walk from the array's starting position, this can be a somewhat expensive iterative process, and for that reason, sometimes more in spatial hashes than in collision detection against a KD tree, you will see people specifying a maximum range for the raycast to check, just so that you don't have to traverse the entire spatial hash if it's a very large world or anything like that. You could say only look ahead 1,000 or 100 or something world space units. I am not implementing that here. That shouldn't be difficult. That should just be a matter of checking how far you are away from the origin, how far the current cell is away from the array's origin, or alternatively, instead of using the raycast against the spatial hash's bounds to figure out where it exits, where its final point is, where its last cell is, you could simply add, and this honestly might be the better way of doing it. You can simply add a certain distance to the array's origin, multiply the array's direction by the max distance, and use that as your last cell. Anyway, that is raycasting against the spatial hash. I have not tested any of this since I started writing it, and it would be a good idea for me to do that soon. First, let me make a commit. This is going to be spatial hash raycast. Incidentally, and I don't know if I should admit to this, because if I do, XOR is probably never going to speak to me again until I do it. But I have never written a ray marcher, and I have been using the metaphor of taking a walk in the direction of the ray from the origin for much of this process, and I believe this is similar to what you would actually do if you wrote a ray marcher in a shader for any reason. Again, I've never done that, so I don't know how accurate that is, but just a minor point of interest. Now, it is a really good thing that I cut off the last video where I did, because I've already been recording this one for an hour, and I still need to bring it into the test world, do some things there, and test it. First, think we're gonna hydrate myself because I've been talking for 2 hours without a break. Anyway, so with all of this done, I can go and let me create a local package. I'm just gonna call this 3D collisions as I've been doing. I'm going to add the collision stuff file of code. Let me save this. I can save this over the one that I've been using. I can open up my 3D collision test world. So here in my collision world test project, I can go ahead and update the collision stuff, and that's going to I deleted the old one. It shouldn't make a difference, but I do like to delete the old version first before I change anything. Nothing that was done to the original collision test world should change. So we should still we should still be able to detect collisions just fine with our old quad tree or oct tree or whatever it was the last time I was messing with this. We can run into things. Apparently the player can't collide with the tree, but I feel like that's because I had the player's like mask exclude the tree, because I can still raycast into it. And can I like, yeah, I can get the ball stuck to the top of the tree and everything. So this is our oct tree world. If I were to change this to instead collision world is going to equal new call spatial hash call what did I call it? Hang on, wait. Call spatial hash node? Why is spatial hash itself not appearing? Oh, call world spatial hash is what I called it. Alright, good job. The only real difference in the way that we would treat the old collision worlds and the spatial hash one is what is going to go into the constructor. So the KD trees took a maximum size, maximum bounds for everything that was going to go in them, because that space was going to be partitioned ahead of time into a tree data structure, and it also took a maximum recursion depth. The spatial hash is not going to be set up like that. The only thing that the spatial hash is going to care about is going to be the chunk size. And exactly what your chunk size should be is kind of a whole thing. I have a lot of small objects. Like I have a lot of objects that are probably 20, 25 world space units in size on average. I'll get into what your chunk size should be later on, but first I just want to run this. I'm just going to very arbitrarily make this 100. So let me run the game. This is going to spatial hash line 83. My vector code really is just like cursed with me forgetting to do simple things that come back to embarrass me later. Anyway, so we can run this, and we are now using the spatial hash, and I can run around into the trees. You can see I am still colliding with trees as I was before. The player's bounding box and the trees' bounding boxes are a little big, but that was a problem that the other versions had as well. The point is I can collide with these just fine. And you may notice that the little red bar at the top of the screen is quite a lot smaller than the little red bar was when we were doing the oct tree. And if I were to raycast, I can cast a ray into the trees, and I'm just going to cast this off in all kinds of directions and hope that we get stuck in the appropriate place. We got stuck on the collision mesh of the tree that time. Very nice. If I try and thread it through some trees, it'll keep going a little bit, but it will eventually get stuck on something like this. If I were to stand all the way up here and just throw the ball off infinitely, it's just going to keep going, and eventually it's going to leave the bounds of the spatial hash, and it'll keep going after that. All right. So aside from me forgetting to feature a few like vector arithmetic functions, this all worked on the first try. All what, 300 something? 301 lines of code for the spatial hashes. That's actually pretty good. I was expecting to have to do more repairs than that. I really hope you appreciate this, because this took a long time to figure out. I had to adapt bits of code from like multiple sources on the internet to get raycasting to work. I will, in case you want to look at a similar library to this, I will leave one of them, the one that I probably use the most of, in the comment. you'll see that I have a lot of code based on this Git repository that's been adapted to GameMaker or have some small changes made. Okay. Spatial hashes, and I will go back into my original project and make sure that my vector code has been updated. Can I take my vector code? Can I update my vector code? Make sure that the scalar versions of add and sub are still there. All right. So that's that. I feel like if I were to go back 2 years ago to the video where I first wrote that, I would see myself saying something like, "Oh, you're never gonna need a scalar version of add or sub." Yes, you will. It's not uncommon, and I'm amazed that that hasn't been a problem until now. So I'm going to mark this as 0.34. We have spatial hashes. That took a lot longer than I thought it was going to. 3 whole videos. So a few more words on spatial hashes, where you would use them versus quad trees. Quad trees are still in use for mesh collisions to organize a triangle mesh into a hierarchy, and I don't foresee that changing. I don't think I would ever use a spatial hash for a 3D collision against a triangle mesh. Like, I guess you can, but I don't see a lot of the benefits to spatial hashes really shining through as much when it comes to mesh collisions, because you tend to have a lot of triangles that are like overlapping or that will span across many cells in the spatial hash, and even in the example over here where I sort of on purpose picked an overly large chunk size, the spatial hash performed quite a lot better than the octree did, because we don't have to do all sorts of shenanigans with like recursively traversing the data structure, and we just have a list of a small number of chunks that we need to check. And triangle meshes tend to not be quite as friendly to that. And I said when I started writing the spatial hash code that my opinion on them has gotten quite a lot more positive as I've been working with them more. And while I do like recursion conceptually, it is often involves doing a little bit more work than certain other iterative methods would entail, and that is certainly true when it comes to spatial hashes. So as for the chunk size that you should use in a spatial hash, I've seen a few different takes on what exactly you should make your chunk size in your spatial hashes. The opinion that I currently like most is that your chunk size should be about 2 or 3 times bigger than, say, an average-sized object in your collision world. And that will hopefully minimize the occurrence of objects spanning multiple cells in the spatial hash. Like, if an object straddles the line between two chunks, then it will be added to both chunks, which is not quite as efficient as it could be. And you want to choose a chunk size that will minimize the occurrence of that, but also not have your chunks be so big that your chunks contain many objects, which is the risk that you run into when you make it too large like this. And if I were to set this to something like, let's say 50, I forget exactly how many world space units a lot of these trees are. I want to say they're like 20 or 30 or so in their side length. You may see even better performance. Although it's honestly a little hard to tell because the red bar is so small to begin with, and at this point most of the frame time in this project is occupied by actually like drawing the trees. But yeah, that is a little word of advice on choosing your chunk size. You are free to argue about that as much as you want in the comments. You are free to try to change my mind on what an ideal chunk size should be in the comments. Yeah, I think that's all I have to say on that matter. So what's next? There is one more thing which I wasn't sure if I was going to cover in this series, and then I asked you all if you wanted to see it, and of course you said yes. I don't know why I thought anyone would say no. And that is using these collision structures for camera free-stream culling. So free-stream culling in GameMaker is kind of a cursed thing. Because GameMaker is so slow in execution, and because figuring out if any given point is within the camera's free-stream is surprisingly expensive. Most attempts at free-stream culling in GameMaker that I've seen are either just like back-of-the-envelope calculations, like using the dot product to figure out if an object is in front of or behind the camera, like I'm using in this project, with questionable results. or they're actually slower than just drawing everything to begin with. But when you use a quadtree or an octree and do a Frustrum culling against that, you can sort of pick out large chunks of the world that should or shouldn't be drawn at a time. And if you have a lot of objects in that collision hierarchy, it's a lot more efficient to do that. And you, at least in some circumstances, could see some performance gains doing that over just drawing everything. So I think I will make a video or two on that. Funnily enough, as much as I've been extolling the virtues of spatial hashes here, I actually don't think it's really that easy to do or that beneficial to do with an actual spatial hash, because shapes of the nature of camera frustrums are a bit of a different breed than shapes of just like a collision sphere or a collision box or anything like that. And then after that, I'm going to dive headfirst into the wonderful, terrifying world of GML micro-optimizations. And there will then be some kind of grand finale video to wrap the whole thing up. And after that, I am never going to talk about 3D collisions in GameMaker again. Good lord. I am so sorry to all those people who were asking me to do native 3D collisions in GameMaker 3 years ago and thought they were just going to get like 1, maybe 2 videos on the subject. Anyway, my name is Michael. I like wizards and dragons and making games. If you want the code for this, look for the GitHub repository down in the video description. I have a Patreon, so if you want to contribute to the channel, links to that can be found in all the usual places. As you can tell, this has been quite a lot of work, so if you wanted to contribute anything, I would definitely appreciate it. Otherwise, I try to post about 2 game dev videos a week, 1 tutorial like this, and 1 Let's Make a Game, currently a 3D wizard game. I hope you all find this useful, and I will see you all later. So, something that I completely forgot to do earlier, that I've been kind of going on about for a few of the previous videos, is to show the debug draw of the spatial hashes. So, if I zoom all the way out in this 3D collision world, and if I hit the F1 key, I've set it so that if I hold F1, we'll do the debug draw. We can see that this is completely and utterly tanking my frame rate. I'm actually surprised that I'm getting frames plural per second and not like seconds plural per frame. But we are drawing not only a red rectangle around each of the spatial hash chunks, but also everything within it, which is what's really tanking the frame rate. There really wasn't any reason to include the collision boxes around the individual objects, but I did just want to do that just for fun. If I run this again and not have it go quite so utterly insane, we can see that we've got ourselves a nice lovely grid. The grid is only really 1 level tall because everything in this world is pretty much just flat on the ground and there really isn't a lot of verticality. But if you did have an object that was somewhat elevated in the air, you would be able to see the cells going upwards in the air as well. The duckling is not part of the collision world. The duckling is simply checking things against the collision world. And if I were to run all the way out to the boundaries, where the trees are a little bit more sparse, over here, for example, and if I were to do that again, you can see that some of the cells that actually don't have anything in them don't have a chunk, have a bounding box around it to begin with, and that is a rather nice optimization. I know I did mention that in earlier videos that cells that didn't have anything would just be like not there, but I do think it's nice to see that visually. So yeah, that's the debug draw. There's really no functional reason to have this in the system, but it does admittedly look quite cool when you're trying to demo it to people. So there's that. Special thanks to Zenjamin, VitroV, Squarecrow, Sindra Larson, Manta Ray, Harold Gidry, GameMaker, Edward Holt, DJ Gibbles, and Army Armbuster for supporting these videos. If you want to contribute to the channel, head on over to the Patreon page down in the video description to join the fun.